Okay, I would like to talk about liveness in L2 protocols, and I'll spend most of my time talking about that, but I do have to talk about my own system for a minute. So my Ethereum Layer 2 system is more secure than others because my system uses a more advanced form of cryptography that's not susceptible to quantum. It employs novel consensus mechanism, more resistant to forks and double spending. And it has a higher degree of decentralization, which makes it more resistant to 51% attacks. But actually, this slide was written by GPT-3. I gave the AI the prompt up at the top and asked it to complete. And this is the completion it gave me, including the bullet points. It somehow knew that I was asking for a PowerPoint slide. So this proves that security shilling can, in fact, be automated. The other interesting thing about this is that according to the makers of GPT-3, they have only trained on data up to 2019. So this is apparently state-of-the-art shilling as of 2019. We'll see what it does when it gets 2022 data. Okay. Having done that, I do want to have one actual security shilling slide before I get on to the more technical topic. About sort of how we think about security in Arbitrum. Arbitrum was designed for security from the beginning. The first part that we designed and built was the fraud-proof mechanism, and everything is really built around the idea of security. Being security researchers, all three of the founders are security researchers, we're very much mindful of the truism in security that it's difficult to build a working system and then graft security on later. So we thought about security sort of from the beginning. Our fraud proofs and all of our security have been not only working, but fully integrated with the system since 2018. We've never released a system without fully working security mechanisms. And that's something that, and we'll never do otherwise. To be a little bit precise about the guarantee that the Arbitrarum protocol gives you, provided that we've implemented it correctly, is that if Ethereum provides safety and liveness, and if at least one honest party is participating in our L2 protocol, then the Arbitrarum protocol guarantees both safety and liveness at L2, including for transfers to and from the L1. So you can always force an exit yourself, according to the protocol design. Okay, with that said, I want to switch to the more generic topic that I'll spend most of my time talking about, which is trustless liveness. This is a really important property of L2 protocols. People tend to focus a lot on the safety guarantees that these protocols give, which are of course really important, right? Safety meaning that the protocol never accepts an invalid transaction, never produces an incorrect result. But liveness is important as well, that the protocol is guaranteed to make progress, regardless of what anyone other than you does. So when I say trustless liveness, what I mean is anyone can force the chain to execute any valid transaction and settle that transaction back to the L1 in practice, not just in theory, but actually in practice. It's a thing that an ordinary person can do, and that they can do at reasonable cost. If the cost is unreasonable, if you need a special purpose supercomputer, you need to buy something new, spend a huge number of CPU cycles, even if you can hire it from AWS or something like that, that's a real impediment in practice. So when I say trustless liveness, I mean this. You can force the chain to execute any valid transaction, settle it to L1, and that's the thing you can really practically do with a reasonable degree of difficulty and cost. Right? And this is often talked about less, but it's an equally important part of this protocol, of these protocols. And this is sometimes discussed as an exit problem. The idea that if you have a fund, say if you have ETH on an L2 chain, that you can get those ETH back to L2. But it's really important that you can force execution of any valid transaction because your assets might be locked up inside of some other vehicle, they might be held in an account inside some dApp, and you need to be able to do everything you can to actually extract your funds if you want to get out. So it's important that it's not just exit of sort of funds held at top level, but it's any valid transaction. Okay, so in order to illustrate some of the issues that come up here, I want to talk a little bit about how Arbitrarum works, although what I describe here would apply to most L2s. I think everything I say about this would apply to Optimism as it's being built, and presumably to ZK systems as well as they get built out. All right, so let me walk through this step by step. This is basically the design of a modern rollup. So you have, on the upper left, you have the sequencer. This might be a single centralized machine, or it might be a distributed system operating on some sort of K out of N trust guarantee or something like that. Its job is to receive transactions submitted by users, either sent directly as transactions signed by an EOA, or perhaps posted on the L1 chain by someone. It takes those and it puts them into order. That's the sequenced transactions up on the upper right. The sequenced transactions then feed into a state transition function, which is a deterministic function depending only on the sequence of transactions and on the state over on the side. So when the chain starts, this state is initialized to something according to the genesis state of that chain, and then the state transition function takes the next transaction and the current state, produces some updates to the state, and perhaps emits an L2 block. But importantly, the state transition function is deterministic and depends only on those inputs. In order to be deterministic, that means it can't peek at the state of the L1 chain or ask what time it is or anything like that. It can only use information that is encoded into those transactions, plus any tags that the sequencer has put on them. And by the way, we don't want to trust the sequencer for anything other than ordering. We don't want to trust it to be truthful about anything else that we can't check. Anyway, the state transition function executes that way. Now, the sequencer has to tell people what its sequence is, and it has to commit the sequence. And it will do that in two stages. The first thing it does is it produces a sequencer feed. This is a feed of transactions that anyone can subscribe to. And so if your transaction is put into the sequence, in a fraction of a second, your transaction will be pushed out on the sequencer feed. And the sequencer feed is a soft guarantee of transaction ordering. That is, the sequencer has that is the sequencer's promise that your transaction will be at that point in the sequence. The sequencer has the power to keep that promise, but the sequencer might be dishonest. If you trust the sequencer's promise, then you already know the transaction sequence. You can execute the state transition function for yourself because it's fully deterministic. And then you know with that soft guarantee what the result of every transaction is in a fraction of a second. If you want a hard guarantee, then you have to wait for the sequencer to post the sequence onto the L1 chain. So every few minutes, the sequencer will take a contiguous batch of transactions, the next ones in the sequence that haven't been posted yet, takes them as a batch, compresses them for efficiency, and then posts them onto the L1 chain. And as soon as that post to the L1 chain has L1 finality, now that part of the sequence of transactions is fully final. And because the state transition function is fully deterministic, the outcome of the transactions is final. At that point, every honest party in the world knows the result, except the L1 Ethereum chain doesn't. Why doesn't it? Well, it can't do what you can do, which is to compute the state transition function on every transaction. Ethereum doesn't have the computational throughput to do that. That's why we have an L2 in the first place. So Ethereum doesn't know, and so therefore you need some other proof protocol to settle those L2 blocks to the L1 chain and get them fully confirmed and notarized. And there you have an optimistic rollup protocol, a ZK rollup protocol, or whatever. We use optimistic, but for our purposes, it just matters that you have a sound protocol for doing this. So this is the basic, operation that all of these systems have. Now, if you want to give a liveness guarantee of trustless liveness, let me talk about a few things that you need to do. One thing that you need to do, is that you need to be able to force your transaction into the sequence. The sequencer might be hostile. It might refuse to put your transaction into the sequence. And so there needs to be some backup mechanism by which you can force your transaction into the sequence no matter what anyone else does. And so what we do in Arbitrarum and what Optimism also does, something like this, is basically if you have an EOA signed transaction, the sequencer seems to be refusing to sequence it, or you just don't trust the sequencer, you can post that onto the L1 chain. It goes into a queue that is managed by the L1 chain. Now, the sequencer, if it's well behaved, will take the items from that queue and merge them into its sequence soon, typically after about 10 minutes, because it's afraid that your write to the L1 chain might get reorged away. But once it's confident that your transaction's been in the queue for more than a reorg interval, it will be happy to include your transaction into its sequence if it's honest. If it's dishonest, after some time interval delta t has passed, then you can do another L1 transaction that forces your queued transaction into the sequence, whether the sequencer likes it or not. That will only happen if the sequencer is either malicious or is down for a long time. But you need to be able to force your transaction into the sequence, even if there is a sequencer. And these chains typically have sequencers because the 1 second soft guarantee is a huge user experience advantage that everyone seems to want. Okay, another thing you need to be able to guarantee is that you're able to settle your transaction to L1, right? So if you can force your transaction into the sequence, then every honest node will see your transaction in the sequence. It will be recorded on the L1 chain. If the sequencer refuses to put it into one of the compressed batches, it'll be in a special batch that you did with that force inclusion operation. But everyone will see it. Every honest node will see your transaction and be able to execute it. And so every honest party will know your transaction happened and what its result was. But you need to be able to settle it back to the L1 because the L1 is the official final archival state of the system. And it's also the one that is used for bridging assets off of the L2 chain. So you need to be able to force, any party needs to be able to force the settlement of valid transactions onto the L1 chain. And by the way, if there's a set of transactions ahead of yours in the sequence, you need to be able to force them on chain too, because they will be settled in order. Okay, right. Also, everyone needs to be able to execute the state transition function. That means that you need to be able to know the state. And so if you're a node who came along late, you need to be able to find out what the current state is. In an optimistic rollup, because all of the inputs, because the genesis state is known and all of the inputs are recorded on the L1 chain, everyone can just play along from the beginning if they want to. And so you need to be able to get the state. That all needs to be possible. Okay, challenges for optimistic rollups. For getting a transaction sequenced, you have the slow path for inclusion. I talked about that. Getting the state, well, you can compute the state yourself if need be, because all of the inputs to the state are recorded on the L1 chain. Or if someone gives you the current state, you can verify that against a hash that's recorded on the L1 chain. Computing the state transition function, well, you can compute that yourself. There needs to be some sort of gas limit system to make sure that you can actually do that on a reasonable node. For settling to L1, it needs to be the case first that anyone can propose a settlement transaction. And then the remaining issue is delay attacks. This is a situation in an optimistic protocol where, remember, in an optimistic protocol, someone posts a claim about what the correct outcome is, someone else can dispute that, and then there's a challenge protocol that goes on to figure out who's right or wrong, and the person who's wrong will get slashed, and then you'll somehow go on. But you need to be careful so it's not the case that a liar who is willing to lose a stake, who is willing to lose stakes, can cause a delay. So for example, it can't be the case that the loser after getting slashed can show up from a different address and make another claim, cause another delay, and burn another stake. Now it's true, for example, the original academic paper version of Arbitrarum had this issue, that a party who was willing to burn an unlimited number of stakes could cause an unlimited delay. But in a production protocol, that's not acceptable. The protocol design needs to be able to establish and prove some kind of maximum on the delay that can be caused, and that maximum needs to be reasonable. It can't be like 8 years, right? And that needs to be the case no matter what Byzantine behavior people engage in, and no matter how much stake malicious adversaries are willing to burn. This is not an easy property to have unless you're very careful about how the protocol is designed. For ZK rollups, you have a different set of challenges. How do you get your transaction sequenced? Well, that'll probably work similarly to optimistic systems. There probably needs to be some sort of mechanism on the L1 chain to demand inclusion, and then if you don't get it, to force inclusion. I'm assuming that that's going to work in the same way because it's hard to think of an alternative. How you get the state? Well, it's easy to get the state if all of the inputs to the state are posted on chain. But many ZK systems talk about what they call compression. which really consists of not putting, in many cases, of not putting all of the inputs to the state transition function on the L1 chain. If they just provide a proof that they know a set of inputs that would produce the current state through valid execution, that's not enough for you to find out the state. And if you don't know the current state, then you can't generate a proof that your transaction, of what the result of your transaction is, and you can't force inclusion. So there needs to be some guarantee of data availability in a ZK system. So it's not trustless if only the prover or the sequencer knows the full state. Computing the state transition function, similar, everyone can do that themselves. And settling to L1, the main issue here for ZK systems is cost and practicality. Can you really compute a ZK proof, not only of your one transaction, but of all of the ones that are queued in front of it in the sequence? Is that something you can really do with equipment that you have, or that you can hire at a cost that a regular person can afford on some external service? If you need to hire 1 million GPUs from Amazon, then you can't really practically do it. So this is the main question, cost and practicality. Can you really do it using stuff that you have? In my view, we don't really know enough about the ZK rollup systems to answer that question. I think this is an excellent question to ask them about what their plans are for this and what they're going to assume. But I think we're going to have to learn about this as we go forward. Okay, I am out of time. I see I'm out of time. I'm happy to talk more about these problems and how you can address them in different systems. I think liveness is an underappreciated aspect of security for these systems, but it is crucial because an attack that can keep you from executing valid transactions, keep you from reclaiming your assets if someone tries to stop you from doing that, is a serious attack, and in many scenarios, it's virtually as bad as one that just openly steals your funds. So I look forward to talking more with folks about this and to engaging with other protocols about this issue going forward. Thanks. We have time for questions? Questions?
Thank you so much. Any questions? Yes, Corey.
You mentioned in the beginning of the talk, it's safe assuming you had the implementation correct.
Yes.
How do you gain confidence that that's so?
It's a few things. One is the code being open and available to everyone to kick the tires on. Number two is the work that we do internally in due diligence, in testing and fuzzing and everything. And the third one is security audits, right? External security audits are key for this stuff. And we do all of those things. And of course, also it's important to have a bug bounty program, so that if someone does discover a critical issue, that they can come to us and that it can be resolved in an effective way. I mean, it's all the things you need in any system, really. And we work to do these things. Other teams work to do these things as well. Thanks.
Thank you. So we do have time for one more question.
Someone to the left of the aisle. Yeah.
Thank you. So I just had one question that kind of dived a little bit more into like the UX of doing an exit for a normal user. Mm-hmm. So assuming the sequencer and any other party that you're relying on isn't trustworthy, what does that actually look like in practice to you, or at least where you think it's going? Like, the example I see is like, for example, Strike and Lightning is kind of the thing in Bitcoin, but you're kind of relying, if you don't know what Strike is, it's like custodial wallet, but they're relying on, you're trusting someone else to run a Lightning node. They have the data. Yeah. How would you avoid that in a rollup situation?
Well, so here's how this works. Assuming that the sequencer is working, assuming that there is a working node that you trust to do it, or that you're willing to run a node yourself, right? That's necessary. So there are a few cases. One case is where you hold ETH in your L2 account. And in that case, there is a precompile you can call to withdraw your ETH to L1. You just call that precompile. Your ETH will get put into a sort of output queue, which is certified by the L2 chain. And then there is an outbox contract on the L1. And so you do that precompile in L1. That sends the certified withdrawal event back to the L1 contract in some sort of, inside of Merkle structure. And then there's some tooling you can use on the L1 after the challenge period has passed. You'll send a transaction to that outbox to claim your funds. And there's tooling that automates that. That's ETH. If you have a token, then you call the token contract, and there's a token bridge. It's a similar system, but there's a token bridge. There's a token bridge contract on L2 that you can use, and it will send a certified cross-chain message down to a buddy contract down on L1, which will release the funds to you after the challenge period has occurred.
Gotcha. So for each of these, it's probably going to be, there's going to be tooling to help people along.
There's tooling.
Like that.
So we have our Arbitrary Bridge tooling, which is a web-based user interface that people can use to do these things. There are other tools that other people have built. I mean, the mechanics of it, the sort of on-chain, on L1, on L2 chain is calls to certain contracts or pre-compiles to say that it happens, and there's UI around that.
Thank you.
Yeah. One more piece of that is, of course, if your funds are in some dApp, then you need to do whatever that dApp needs to get them back into your account, But that's the same as on L1. Thanks.